Okay, so now we're going to talk a little bit about balancing. The law of conservation of mass states that matter cannot be created or destroyed. And we want to follow these laws of conservation of mass because we're here in this universe. So what we're going to do is learn how to balance. We need to have the same amount of mass before the reaction as we have after it in these alpha, beta, and gamma, alpha, beta decays. So in these, when we're balancing, always, not just in alpha, beta, the starting materials are called the reactants and the ending materials are called products. So what I want everyone to do is think about treating the arrow, this arrow right here, treat that like it's a plus sign, okay, or an equal sign rather. So I know it says it's an arrow, but think of it as an equal sign. So the starting materials are the reactants. So where you start, what you're putting into it. So here are your reactants. These are our reactants. These are my products. And instead of thinking of this as an arrow, think of it as an equal sign. And then it is a little more easy to think about it like algebra, right? So over here it says, and just take it one part at a time. So think to yourself, 222 is equal to 4 plus 218, and that is true. So if you're thinking about this top part, is equal to 4 plus 218. And it is true, 218 plus 4 is equal to 222. Same thing with the bottom part. So 88 is equal to 2 plus 86. That's true. There are 3 steps when you're balancing these. The first is that you want to balance the mass number, which is the number on top. So over here, I'm going to look at these numbers first. Remember, treat it like an equal sign, not an arrow. 232 is equal to 228 plus something. We'll work backwards. Think to yourself, you can either subtract it like algebra, right? Set up an algebraic equation, or just work backwards. What do you need to add to 228 to equal 232? That's going to be 4. Okay? And then the next thing you want to do is to balance the bottom number, right? So that's the atomic number. So you want to think same thing. 90 is equal to 88 plus something. Okay, think about it like algebra. So you can say like 90 is equal to 88 plus x. So 88 plus what is equal to 90? That would be 2. And the last step is to just fill in your symbol. So once you know you've done this, the hard part, then you just need to think about the different symbols for each type of radiation that we previously talked about. This looks exactly like that, an alpha radiation to me, that HE. So I'm going to put in this HE symbol that we talked about previously. And that's it. So first you balance your mass, then you balance the atomic number, then you figure out which symbol to use, okay? The bottom number, of course, is the atomic mass. That will tell you which symbol to use. So alpha will always have that 4 and 2, beta will always have that 0 and the -1, and then you know to put in the E. And that's it. It's pretty simple. It sounds complicated, but it's pretty easy to do. Just takes a little bit of practice. So we're going to practice a little bit. All right. So on this first one thing I want to think about is thinking, remember this is an arrow on your paper, but we're going to think about it as an equal sign. Equal sign. So 9, first thing I notice here, I'm going to start with the top number, just like the previous slide said. 9 is equal to 9. Did anything change? Does 9 equal 9? Yes, it sure does. So over here, I'm going to write a 0. There's no difference. Then we want to think about what's happening on this side. So I've got 3 is equal to 4. Is that true? Does 4 equal 3? No, so something changed, right? So what do you need to add to 4 to make it equal negative, or to make it equal 3, right? 3, or think about it like algebra. 3 is equal to 4 plus x. Now, some of you might be tempted to say 1, but then I want you to think about how I solved it. Is 4 plus 1 3? No, it is not. It's actually negative 1, right? So we're going to put in the 0 on top, a negative 1 on the bottom, and then I'm going to think about what does that look like? That looks like beta. And that's a very messy little e, but the beta symbol, if you remember from what we did before, this is our symbol types. So this is our beta radiation. It's a little e. So our number of protons changed by 1. Our mass number did not change at all, and we symbolize that with an e. Okay. So the next one, we just have to do the exact same process, right? So we're going to say, I'm going to look at what's on each side, the reactants and the products. I'm going to write in an equal sign, so I remember that it's essentially equal. And then you're going to look and see what it's telling you. Follow the clues. So I'm going to start with what's on top. 1. So 1 plus what is equal to 140? That would be 139. Just make it equal. 139. 139 plus 1 is equal to 140. That's true. Now I'm going to look on this side again and say, okay, on the left, on my reactant side, it says 62. So I need them to be equal. So on the right side, this also needs to be 62. And so far, all I have is 0. So this is going to be 62, because 62 plus 0 is equal to, if I'm going back to the other side, 62. So that's this neutron emission in which the number of protons does not change, just the weight is changing. So my symbol doesn't have to change. My symbol is SM. So I'll write it again out here so it's a little more neat. 139, 62. Okay, very good. All right, number 3. Just like before, I'm going to make this an equal sign. So 209 is equal to something plus 4,2He. So really just think about it as, I'm going to do my mass number first. 209 is equal to some number plus 4. So if I was solving for x, I know I could take this 4 and just move it to the other side to give me my answer. So it's 209 minus 4 is 205. All right, now I'm going to do the same thing for the atomic number, 83. 83 is equal to some number x plus 2. So I'm going to move the 2 over to give me 81, right? And then if I'm going back to check myself, I can think to myself, does this make sense? Is what I'm saying true? And it is true. 81 plus 2 is equal to 83. So now we want to be careful though, because as we've talked about, anytime you change the number of protons, which we have, we went from 83 protons on the left to 81, it changes the element itself. So I need to make sure to grab a periodic table because I need to write down what this element is now. Okay, so we were at 83, which is bismuth. And so I need to find the atomic number 81 to get my new element. So I'm looking. There it is, it's thallium. Thallium's 81. So TL, not TI, because that's titanium. So this is an L. Sometimes I add a little tail. All right, let's keep going. Well, there it is. Okay, next one. This is the same process, but we're gonna just start on the other side. I actually think, oh, I just gave them away. I actually think sometimes it's easier this direction because you just have to think about, you already have what happened before. Okay, so equals, think about your equal sign, 238 plus 4. Okay, what is 238 plus 4? Well, that is 242. What is 92 plus 2? That is 94. And again, we need to change over because 94 protons is not the same as 92. This is not U anymore, okay? That's not uranium. We need to find 94, and that is plutonium, number 94. That's plutonium. PU. PU. Okay, so next one. Start with the top. 53 is equal to 0 plus 53, right? 23 is equal to -1 plus something. Now, I sometimes think it's easier to work backwards because a lot of times students will be like, oh, 22, and they'll put that in there. But 22 plus a -1 is not 23, right? 24 plus a -1 is 23. So work backwards and see, does this make sense? What I'm plugging in, is it making sense? So again, if you change the number of protons, it changes the element itself. So I don't want to leave it as a V. I don't want to leave it. I'm going to go over to my periodic table. I'm going to find number 24. It is chromium, which is Cr. Okay. Once again, 11 plus 0. 11 plus 0 is 11. 6 plus a -1 is 5. Okay, and we've changed the element itself. It is no longer carbon, now it is boron. Okay, so we're going to change gears a little bit and quickly talk about fission and fusion reactions. The best way I can tell you is fission, think fission, division, okay? Fission, division. In a fission reaction, things are going to be getting, we're going to go from something very like large and heavy, and it's going to be unstable, so it will split. to make up for being too heavy into smaller parts, make it lighter and more stable. Okay, sorry, had to quiet my daughter. Fission reactions release a huge amount of energy. Okay, these are what are going to power nuclear bombs. These are very, very, very powerful reactions. Nuclear power plants, that's fission, a fission reaction. Huge amounts of energy released, very powerful. A fusion reaction is the opposite. Okay, instead of something that is really heavy splitting apart, it'll be something that is light. Okay, so something when, remember we were talking about alpha and beta, I said atoms are always trying to get to their Goldilocks just right phase. So if something's too light, it is unhappy just as much, unstable, unhappy just as much as if it is too big and too heavy. So what can they do? They'll fuse together to make something more heavy and more stable. So fission, division, and fusion, you want to think coming together. Make it more heavy. Fusion is the nuclear reaction in which the two or more atoms fuse together to create an atom that has a heavier nucleus. And these are what is behind the power in the sun. The sun is a result, and all, not just the sun, but the stars in the sky are all the results of fusion reactions. So it's usually an unstable hydrogen fusing with another unstable hydrogen to create helium. These are these names are isotopes of hydrogen. They do not produce radioactive products. Unlike fission, which is very radioactive, a lot of that gamma radiation, fusion reactions don't have that. Okay, not radioactive, but still very, very powerful. Okay, so fission reactions. Fissions break up the nucleus. Fission, division, think that. You get one large atom and break it up into smaller parts. This is what happens in atomic bombs, and it's also used in nuclear power plants. This produces a lot of dangerous gamma radiation along with alpha and beta radiation because remember, when gamma radiation occurs, alpha and beta tend to follow behind that. So this is pretty bad stuff when this happens. It can be pretty dangerous. Fusion reactions, on the other hand, are what occurs in our stars and also in hydrogen bombs. It happens when atomic nuclei come together that if they are too lightweight and they are unstable, they will fuse together and become more stable. Not much gamma radiation is produced, but a whole lot of energy. All right, and we'll insert a clip later of these fusion versus fission reactions. Great job.